You're sitting by the window, the aircraft starts its takeoff roll. Within seconds, you're doing 270 kilometers per hour down that runway. And the only thing between that aircraft and the tarmac? 4 sets of rubber tires. The same basic concept as the tires on your car. Except nothing about them is the same. These are some of the most engineered components on the entire aircraft. And most people never give them a second thought. Today, that changes. Let's start with the numbers, because they're the fastest way to understand what aircraft tires are actually dealing with. A typical commercial aircraft tire is inflated to around 200 pounds per square inch. Your car tire runs at roughly 35 pounds per square inch. That's nearly 6 times the pressure. A single main gear tire on a Boeing 747 carries approximately 26,000 kilograms of load. On landing, that tire accelerates from a complete standstill to around 270 kilometers per hour in under 1 second. The friction heat generated in that moment is enormous. And yet the tire holds every time. That's not luck, that's engineering. So, what makes an aircraft tire capable of handling those numbers? It starts with construction. Aircraft tires are radial or bias ply construction. Layers of nylon cord fabric built up in a precise sequence, bonded together with rubber compound, wrapped around a steel bead that locks the tire onto the wheel rim. The tread itself looks almost slick compared to a car tire. No deep grooves, no aggressive pattern. That's intentional. Aircraft tires are designed to channel water through shallow circumferential grooves, enough to prevent aquaplaning at high speed without sacrificing structural integrity. The carcass, the internal structure, is what carries the load. The tread is almost secondary. And running through all of it, multiple layers of reinforcement built to withstand pressure, heat, and impact simultaneously. Here's something most passengers don't know. Aircraft tires are not inflated with air, they're inflated with nitrogen. And there's a very specific reason for that. Regular air contains moisture. At altitude, temperatures drop significantly. Moisture inside a tire at altitude can freeze, expand, and cause unpredictable pressure changes. Nitrogen is dry, inert, stable across a wide temperature range. It doesn't support combustion, which matters enormously if a tire overheats on landing or during a rejected takeoff. It doesn't degrade rubber the way oxygen does over time. The pressure remains consistent whether the aircraft is sitting on the ground in Dubai at 45 degrees or descending into London at -30. Nitrogen is not a shortcut, it is the correct engineering choice. Let's talk about what actually happens on landing. The aircraft crosses the threshold. Main gear touches down. At that moment, the tires are stationary. The aircraft is not. The contact patch hits the runway and the tire has to spin up from 0 to touchdown speed in a fraction of a second. You can see the smoke. That's rubber being scrubbed off the tire surface as it accelerates. Every landing does this. Every single one. Then the brakes are applied. The anti-skid system modulates brake pressure to prevent the tire locking up. The same principle as ABS on your car, but operating at far higher loads and speeds. The tire absorbs braking energy, cornering loads, and the full weight of the aircraft simultaneously. By the time the aircraft reaches taxi speed, the tire has already done the hardest work of the entire flight. Now, the AME perspective. Tire inspection is part of every walk-around check, conducted by flight crew or maintenance personnel, depending on the operator. But what are they actually looking for? Cuts and gashes. Any penetration of the tread or sidewall that reaches the carcass is a rejection. Flat spots, caused by a locked wheel on landing. Evidence of anti-skid system failure or hard braking. Wear indicators? Yai. Aircraft tires have built-in wear markers. When the tread wears to those indicators, the tire is removed from service. Bulges? A bulge in the sidewall means internal structural damage. The tire comes off immediately. Creep marks. A colored line painted across the tire and wheel rim. If those marks no longer align, the tire has moved on the rim. Pressure has been lost. That aircraft does not fly until it is rectified. Here's something that surprises most people. Aircraft tires are retreaded multiple times. A new aircraft tire is expensive, several hundred to over $1,000 depending on type. But the carcass, the internal structure, is built to last far longer than the tread. When the tread wears to limits, the tire is removed, inspected, the old tread buffed off, new rubber applied, and the tire is returned to service. A commercial aircraft tire can be retreaded multiple times before the carcass reaches its limit. Each retread is subject to the same certification and inspection standards as a new tire. This is not a cost-cutting measure. It is an approved, regulated, and entirely safe process used by every major airline in the world. What happens if a tire fails? Aircraft are certified to handle it. Multi-wheel bogies, the gear assemblies with multiple tires, are designed so that the loss of one tire does not compromise the ability to land or stop the aircraft safely. The loads redistribute across the remaining tires. The aircraft can continue to a safe stop. A tire blowout on an aircraft is not the same as a blowout on your car. It is a managed, anticipated failure mode that the aircraft and its systems are designed to handle. That said, a blowout is still a serious event. It will trigger an inspection of all remaining tires, the wheel, the brake assembly, and the gear structure before that aircraft flies again. Nothing gets signed off until everything is checked. As an AME, I have changed aircraft tires on the line in the middle of the night with a departure time ticking. I have rejected tires that looked acceptable to the untrained eye, a cut that hadn't quite reached the carcass, a creep mark that had shifted 2 millimeters. 2 millimeters. The passenger never knows. The crew never knows. The flight departs on time and nobody thinks about the tires again. That is exactly how it should work. The engineering is invisible when it's done correctly. The inspection is invisible when it's done correctly. The only time anyone notices the tires is when something goes wrong. My job, and the job of every AME on every ramp in the world, is to make sure that never happens. So next time you're sitting by that window watching the landing gear come down, you'll know exactly what those tires are about to do. If this gave you a new appreciation for what's holding that aircraft up, hit subscribe. I break down aviation in a way that actually makes sense. See you in the next one.